All right. Good morning, everyone. 大家好. I'm going to be presenting in English because, much of the technical terms are not very familiar in Chinese. So let's go with that. Hopefully everyone's okay with it. So as mentioned, I've been a very heavy Kaggler for a few years. And through my experience on Kaggle, I've learned a lot of tricks that then I can apply to real-life problems and also research problems that I work on during my job. So the topic of this presentation is machine learning for optimization problems. Now, if you're familiar with academic research, you probably know that there's people doing optimization, there's people doing machine learning, there's people who do optimization and apply that to machine learning, but there's nobody who do machine learning and then apply that to optimization. So this is something that I will talk about, at least for a specific type of optimization problems. So if you think about real-life optimization problems, the basic idea is to improve efficiency of some kind of system, such as buying a portfolio of stocks, hiring a set of job candidates, preparing the shortest route for deliveries, etc. Now, some of these problems involve a large number of decision variables. So if you think about designing roads and intersections, right? If you look at a large city like Beijing, for example, and you want to design the roads in a way that you minimize the travel time, you minimize the traffic congestion, etc., you have a lot of different variables to consider, and this is a problem that's not very easy to solve using traditional optimization methods. So the goal, of course, is to maximize something, which we can call a reward or some kind of value, while minimizing something else, which we typically call cost. So again, if you think about designing roads, then you want to perhaps minimize the congestion, which is a cost, and you want to maximize the number of cars that can fit into your system at any given point in time. So there are basically three categories of solution approaches. Okay? So the first category is linear optimization. Sometimes it's also called linear programming. And the basic idea is if you formulate the problem as some kind of linear objective and a set of linear constraints, then you can solve that somewhat easily with existing technology. Then there's also dynamic optimization, which works for a specific subset of problems. And the idea is that you start from the end of the problem and then you work backwards to the start. And you can chain together optimal decisions from each step of the way. And it's fairly fast if the state space is small. So for those of you who know about reinforcement learning, that's also a dynamic optimization technique. And if you think about the game of Go, how AlphaGo works, in that case, the state space is actually quite large, but if you do it in a smart way, namely with deep learning, then you can kind of reduce state space in certain ways. And that works quite well as well, but it is quite difficult to model and to implement. Then there's nonlinear optimization, so that includes things like evolutionary algorithms, like genetic algorithms, and also simulated annealing. Again, these are perhaps more theoretical in nature, and it's not always easy to apply these techniques in real life to real life problems. So many real life problems are not easily abstracted into these kinds of formulations. So what is simulation optimization then? So for those of you who are not familiar, the idea of simulation optimization is, first, I'm going to build a simulation of my real-life problem. So if you think about traffic, congestion, and designing roads, well, you can have a simulation of a city, like Beijing, for example, right? And you have cars that go from point A to point B, you have roads in the system, you have various intersections, you have various designs. If you have a software simulation, then you can just run it through and see, okay, with this design, what performance will I get? And the idea of simulation optimization then is, Okay, if you try design in a trial and error fashion, then you can eventually come to some kind of a optimal or some kind of good enough setup for your problem. And also, if you think about tuning hyperparameters in machine learning models, while that's not really simulation, but the idea of trial and error is also how, to a certain degree, simulation optimization works. Now the problem with that, of course, is very time consuming, right? So if it takes you, let's say, 3 hours to run your simulation once, and you're using it to do trial and error running experiments to look for optimal decisions, then that might take more time than you have. And that's often a problem in real life with simulation optimization. And there are certain different techniques to try to get around that. So you can do things like equation optimization, where instead of going through all possible decisions, you look for smart ones to try. So how does machine learning play a role in this problem then, right? So you have this simulation. It's typically fairly large and it takes a while to run. But is there some way that you can use machine learning to help make this better, faster, etc.? So the idea here is to use machine learning to model the simulation. Okay? Now, if you think about real life, right? If you have some kind of problem where you're predicting, is this picture a cat or a dog? You're essentially trying to model some kind of human decision process, or just some kind of decision process. Okay. Now, if you want to say, is this particular set of decisions in my simulation going to lead to good or bad performance? Well, you can actually use a machine learning model to model the simulation. So if you can do that, then you can actually reduce the complexity of the simulation to the complexity of the machine learning model. So how would this work then? So first, you can simulate a large number of samples using a good distribution of decision variables. So if you think about, again, the traffic problem, maybe you want to consider certain variables like where do I put an intersection, where do I make new roads, where do I extend the width of roads, and you want to just sample simulation results using a good distribution of different values for these variables. Then you want to evaluate the performance of, you want to evaluate the performance metrics of interest. So for example, how much congestion is there in the road if you do that? How many cars am I able to fit? How long is the travel time for cars on average in my simulation, etc. And then you want to train machine learning models to predict performance from inputs of decision variables. So given this simulation that I have, now let's say I have a specific set of decision variables, which is I will put 5 intersections into my simulated city. I will make my road width on average 4 lanes. I will decide to have a city, that's let's say of a certain size. So given these decision variables, I can then try to predict the performance within my simulation using a machine learning model. And then finally, you can build some kind of an optimization procedure after that to then look for decisions that can lead to the best predicted performance. So this is like a general framework that you can think of when using machine learning to solve certain optimization problems in particular simulations where you can, in essence, generate as many samples as you want so you don't have a problem with data. And as long as you can come up with a good model to reproduce a simulation, then the machine learning model should be very good for doing optimization. Now this is still computationally challenging because ultimately what you start with was probably an NP-hard problem, and what you have is still an NP-hard problem. The idea of searching for possible decisions out of infinite number of possibilities is extremely challenging, but when you can reduce the computation time by some kind of linear factor, that could still be very useful in practice. So here we have a case on workforce planning. And the specific setting is call centers or contact centers. And how contact centers work is that, if you have a company like Alibaba or Air China, right, and people have problems with their product or they have certain questions, they're going to call in or they're going to send a message into some kind of a customer service center, and then the customer service center will try to help solve the problems. And usually it is humans who are working at these customer service centers. And then this idea of workforce planning is to assign the right number of workers with the right type of skills to certain shifts so that you can essentially maximize the number of people that you can help while minimizing the cost of having all the workers. So this is globally a $200 billion business, and much of this is outsourced to countries like the Philippines, but within the US and also within China, there's still a large number of people working in these contact centers. And basically, staffing costs account for about 60 to 70% of the operational costs. So you can imagine that in terms of workforce planning, this is one of the settings where it has a lot of monetary value. So modern contact centers, they provide service in multiple channels. So typically you think of handling phone calls, basically customers calling in to these contact centers, and then some agent will pick up the phone and answer your questions. But now there's also live chats, there's telephone, there's email, there's SMS. So I can just send a WeChat message to some kind of a customer service outlet, and then they will try to answer my questions. And also they handle multiple languages, right? So a lot of companies, they don't have customers who only speak one language. Maybe they have customers who speak English and Chinese and French, etc. So you do need agents who are able to handle different kinds of languages beyond just one that they speak. And of course, as I mentioned, the problem is to determine the right number of agents with the right skills to meet performance requirements. So some of your agents might speak English, some of the agents might speak Chinese, some of the agents might speak both, some might speak French, etc. Right? So there are a large number of different skills that agents may have and that your customers may need. And there are different customers that come in all the time. So you need to have some kind of a schedule of your workforce in order to have the best service at minimal costs. So how do contact centers work then? Right. So a caller calls in. Let's say I have a problem with my flight. I want to call in to Air China and I want to ask them about rebooking my flight to a different time. Then within the system, they'll first ask you, okay, what language of service do you need? Is it English? Is it French, Chinese, Spanish, Arabic, etc.? And once you answer that question, usually by pressing a button in the phone, then they'll ask you another question. So what's the problem? Is it about bookings? Is it about refunds? Is it cancellations, special needs, complaints? Again, there's many different possible services that you might need, and often that's because an agent may know about bookings but does not know about complaints, or they may know about special needs, etc. And after I let them know about what my needs are, then I'm routed to the eventual agent or the eventual group of agents that handle my language and also handle the actual service that I need. And if there's nobody in front of me, the agent will pick up the phone and try to solve my problem. But if there's people in front of me, then I get put into a queue and I have to wait for a certain amount of time until the agent is free again and is able to help me. So you can imagine that if the demand for service is very large and there are not enough agents, then there'll be a long queue and the customers will be very unhappy. Right, so what's the optimization problem? Well, as I just mentioned, if the demand is high and agents are low, customers are unhappy. But alternatively, if the demand is low and there are a large number of agents working, then they're just sitting there and they have nothing to do and you're paying for nothing. So in both cases, it's less optimal, and as the manager of the contact center, you want to have the right number of agents working at any given time. So as I mentioned many times, these agents, they have different skills, and they have multiple skills as well. And they have different costs, right? So you can imagine that the agent who speaks 5 different languages and understands 3 different parts of the system, they might cost 3 times more than an agent that only speaks 1 language and only understands 1 part of the system. So it's a very complex problem where you have agents with multiple skills, different costs, and you have customers with different needs, and they arrive in different times. And typically, there are many different performance metrics, but the one that's most often used is called service level. And service level is the percent of customers that are waiting for more than a certain number of seconds before they're helped. So oftentimes it is something like, okay, 70% of the customers must wait less than 30 seconds before an agent is able to answer the phone. So you must have enough capacity, enough people working in order to meet a pre-agreed service level. So that's the general problem framework. So then what is staffing and scheduling? Well, staffing and scheduling is assigning agents to work in specific shifts. So a shift could be 9 a.m. to 5 p.m. like what you would see in some countries, and then they work from Monday to Friday. But it could also be from 9 a.m. to 9 p.m. It could be from midnight to 8 a.m. So there are many different shifts that are possible, right? And the shifts are configurable, so the model has to be flexible. You can't just assume that everybody works in the exact same shifts. And customer demand and service requirements, they do change over time. So for example, for some type of companies, they will have a lot of customer demand in the mornings. For other companies, it will be in the evenings, and then for certain companies, there will be more demand during certain times due to special events or other reasons. And of course, the agents are limited in who they can service. So if you have an agent who only speaks English, that agent, of course, is unable to help a customer who only speaks Chinese. So why do you need simulation for this problem, right? I mean, why can't I just do linear optimization or dynamic optimization or some other, use some other solution to come up with good shifts to schedule to my agents? Well, it turns out that service level is actually very difficult to model mathematically. Okay? So you can imagine that if I have a contact center, adding 1 additional agent might improve their service level, or it might not, right? So if I add another agent that only speaks English, but most of my demand is customers who speak Chinese, then of course I won't improve service level because my agent cannot be very helpful, right? But maybe adding another English-speaking agent does allow more of the capacity from your Chinese-speaking agents to help, to allow the capacity of your English and Chinese-speaking agents to help the Chinese customers only, right? So you're shifting the capacity a bit, and that will still improve service level. So there are many different ways that adding 1 agent can improve service level, and it's not always clear how this effect takes place. And that's why it's actually very difficult to model this mathematically. And also, if I have a lot of agents at 9 in the morning, they might not be useful for handling customers that arrive later on, right? So maybe at 11 a.m. So again, it's not clear how this works. And now in modern contact centers, because you have people who are sending emails and people who are chatting with the agents, it's even more difficult to understand how service level is affected. Okay? So with phone calls, there's a lot of theory behind how phone calls are handled, and you can model this more or less with what's called queuing theory. But with emails and chats, it's harder because when an email comes in, right, the agent doesn't have to reply immediately, whereas when a phone call comes in, the agent has to answer the call as soon as possible. With emails, maybe I can wait 5 hours before replying because right now I'm busy handling calls from customers who are calling in. So again, this makes it even more difficult to model mathematically, and as a result, it's very hard to find even academic literature on solutions for this problem, even though the field of contact center optimization and queuing theory is one of the larger fields in research areas. So it turns out that simulation optimization works quite well for this problem. Now there are some other techniques that may work, but it's really not known by the community. The issue with simulation optimization for this problem, and kind of as I mentioned in general, is that it's fairly slow and it may not give optimal results. So the question that we have then is, can we do better? So let me start by saying that I do applied machine learning, and I have very limited knowledge of how optimization works. Okay. So those of you who are here right now, you might have just as much understanding of linear optimization or dynamic optimization as I do, or you might even have more. So I come into this problem without a very good understanding of optimization, but I have a very strong understanding of machine learning. And how this came about was my PhD supervisor, he once presented this contact center problem in our seminar, and after hearing about it, I thought, okay, this is something that we can solve with machine learning, right? So this goes into how, as people who do data science and machine learning, how you can apply some of your knowledge and skills to help your company solve real-life business problems that might not, at first glance, be obvious as machine learning problems. So the idea is this. Can we build a machine learning model to quickly and accurately predict service level for any given staffing schedule without knowing about the dynamics? Okay. And if we can do that, then we can predict the service level for many schedules and just take the best one, right? So in a simulation, if you ask a simulation and say, what is the performance if I have this many employees of these types of skills, the simulation can tell you, okay, the performance will be this much. And you will get the result maybe in 10 seconds. But, as you know with machine learning models, right, if you ask XGBoost this question, XGBoost will give it to you in 30 milliseconds or 3 milliseconds. And that's what we're going after, right? If we can get this in 3 or 30 milliseconds, then we can ask many more different questions. We can get many more results instead of just using the simulations. So then, in a figure, you have these staffing schedules that come in, they go into a machine learning model, then they go into a deterministic optimization framework, and then you get the best staffing schedule. So that was our approach. Now, for the interest of time, I'll go a little faster from now on. But the idea is you start with a simulation that models the system well, right? You sample solutions offline, you train a machine learning model on the simulated samples, and then you can use deterministic optimization to find good solutions from machine learning predictions. And, well, what's our machine learning model in this case then? Well, we're going to use LightGBM, so thanks to the Microsoft guys. And here's a set of features that we create for this problem. Now remember, what we start with is just a staffing schedule. So how many agents do I want with different skills working in different time periods over a 1 week large period? And we can break that down into things like total agent cost. So it comes down to feature engineering. The total agent cost, total agent count It's just a total number of agents that you have working in total, and then you have number of agents per group, number of agents per shift, per interval, per group, per interval. So in total, you could have something like 1,500 features for a very simple, fairly simple contact center. And that's exactly what we do. So we have set up a numerical experiment with 5 customer classes and 5 agent skill groups, and it's only based on language. And there's also email and chat, and we'll simulate a time period of 1 week to see how well each particular schedule works. Sorry. And then we compute a service level for each customer class. Then we get to prediction performance. So we simulated 90,000 samples, trained the LightGBM on 60,000, and evaluate on the other 30,000. And you can see that in the GBDT row, we have RMSE of about 2 to 5% for these different skills. And then we have an R-square that's well over 0.9 and sometimes 0.99 for some of the skills. And this is very important because if your machine learning model does not predict very well the target, then you can't do a very good job of simulate or optimizing for the best results. But imagine if your machine learning model perfectly fits the simulation, then you can use that instead of the simulation itself to optimize for performance. So let me skip how we do the optimization. It's very simple, and we use a local search algorithm where you can just use some kind of deterministic search algorithm. And let me show you some of the results that we got. So we already had a simulation package that was built for this problem, and then we also had a simulation optimization package that was also built. And with simulation optimization, we performed 100 runs with different starting schedules, and it took about 3 minutes per run. Okay, and in total, that's about 5 hours. And we get this schedule that has an objective score of 129. Now, it doesn't matter what exactly the value is. In this case, the lower the better. Basically, 129 is a combination of meeting the service level requirements and also minimizing the cost. And the cost is just 1 unit for some agents, 1.5 units for some other agents. And out of these 100 runs, basically each run you get 1 optimized result. And the best one is 129, and the median score is 135.5. Now, the same problem, if we use machine learning optimization, it takes about 2 minutes total. So we have trained the model before already. Okay. The idea is that you train the model before offline, and then you can just use the trained model to make predictions on service levels and then optimize over that. And it takes about 2 minutes to do the optimization with machine learning model, and we get an objective score of 120. So that's an improvement of maybe 6, 7, 8% or so. And in the world of contact centers, that's quite substantial, right? Because that almost translates directly to a 5% reduction in costs. Right. So, yeah, well, in conclusion, many real-world optimization problems are difficult to solve mathematically. Now, you learn in school that, okay, there's all these great optimization techniques, but using them in practice is often very hard. Simulation optimization is a very good option because you can apply a lot of the realism of your actual problem, but it is very slow. However, machine learning can be used to fit the simulation, and it provides a very fast alternative, and we apply this approach to the contact center scheduling and staffing problem, and we can find an improved solution that's about 7% better and decrease the runtime by over 100-fold. And you can apply this approach to other challenging problems as well. So for example, scheduling appointments for medical patients to use MRI machines or to see doctors, or in transportation systems design, and there's many different other problems that use this approach. In the biology area, people are using this for certain type of biological simulations, in chemistry for certain chemical simulations as well. So this is starting to become more popular, but I think in the general field of management and business, we're basically the first to look into this. So that's all from me. Thank you.
Thank you so much, Professor Wang. And we have another 14 minutes for the question and answer process. 谢谢王教授。然后我们接下来有14分钟的这个问答时间。请感兴趣的这个朋友举手发言。对。
Okay, thanks for the presentation. It's crystal clear. So thank you very much. But I'm not really agree with your first point. So apply machine learning in optimization is not really a new idea, right? So basically, Bayesian optimization is a good example, right? So we use, for example, Gaussian process to perform a regression, and we predict not only the mean but also the variance, and we can calculate the acquisition function and everything, and then we perform optimization. So, so my question is, so no matter how you train your machine learning model, how good your machine model it is, but your machine learning model cannot be as accurate as your simulation. So, so there is a compromise to do, right? So you train your machine learning model offline, and then you just use that to perform optimization. Yeah, I agree it works on this example, but it may not work on other examples. So what do you think about the offline training and the online training, the dynamic adjustment of your machine learning model and all this kind of stuff, and their application in real world optimization product? So that's my question. So thanks.
Yeah. So that's a very good question, actually. The key. Okay, I can't go back now. The key to all of this is how well does your machine learning model fit the simulation, right? Now, it turns out in the problem of workforce planning, with the right features, so the right feature engineering, we can get within 2% of the simulation outcome, which is very good. But what we started with, so if you, instead of using, let's say, gradient boosted trees on this problem, then you were to use